Hello class, my name is Dr. Arthur Ngomo Mari. I'm going to teaching you basics of electricity with the combination number EE8104. So before starting doing this series of lectures, I'll start to show you the assessment plan or study guide which we are going to use during the entire semester. As you know that this semester has got 15 weeks, and therefore I also divide it in 16 weeks. This is the study guide and assessment plan. My name is Arthur Ngomo Mari, and it was prepared in this November this year. Starting from this module is EE8104 is a module in which the basic of electrical engineering is studied in this subject. The main objective is to establish the competence to students so as to establish fundamental principles related to competence involving electrical and electronics engineering field. Hello? The aim of this module is to enable learners to have a sound and well-articulated technical education built on the strong foundation of scientific principles and electrical engineering, to enable learners to have adequate personal skills that can allow to create sustainable and effective self-employment opportunity, and to enable learners in challenging and stimulating environment which will motivate to realize their technical potential in course of their studies and equip them with knowledge and skill needed to maintain up-to-date education throughout their career. And the objective, as you can see here, to establish sound foundation of scientific principles applied in the field of electrical and electronics engineering, to create awareness and the need of being creative, innovative, and self-reliant in tracking electrical and electronics engineering problems, and to develop the ability in communicating with the workmates in all levels to create conductive working environment within the field of electrical engineering. The assessment of this subject will go according to the university guideline, as you see in your prospectus. So the marks graded is, as you can see here, A, B, B plus, C, D, F, and I. And my contact is the wing A in basement of electrical wing, room number 13 basement, or wing D, room number 21 in architecture basement. And lecture will be as per timetable, so please prepare to do this lecture as per timetable. And also for the case of continuous assessment, we'll have two tests, the one and 4 homeworks. This will be assessment. And homeworks and the assignment will have 15 marks, and the test will have 25 marks. Classroom test will be the 2 hours test, and it will be guided as we did in the examination. But the assignment will do it by your own, and you will collect. And for the case of you are online, we can also communicate through Moodle. Semester examination will be at 17th week, and this will be administered by the Department of Examination of the university. So the module itself, as you see, it has got 6 credits. 6 credits, and that means we will have 4 hours every week. We have 2 hours lectures every week for 15 weeks, and also we'll have 2 hours tutorial. The content is, as you can see here, current electricity, SI units. So we start with the SI unit, then we come with the current electricity, and after current electricity, we start the DC network, whereby we will see different kinds of these laws, like Ohm's law, Kirchhoff's current law, Kirchhoff voltage law, Thevenin theorems and superposition theorems, series and parallel circuit, and power DC. All those we are going to deal regarding DC. And in AC, we are going to see the circuit laws and theorems, single phase, series, and the parallel circuit, three-phase system, and the application of complex number. AC theory also we are going to discuss about single phase and polyphase circuits, and also the last chapter will be, the last topic will be the magnetic circuits. Okay. In magnetic circuits, of course, this is a list of reference we are going to study. And also here I just divide my topics according to weeks. We have 15 weeks in studying, and therefore lecture 1 will cover system units, current, electricity. As you say, lecture 2 will be the DC. We'll have AC circuits, and also in assignment, this will do also for lecture 1 and lecture 2, we have an assignment, and then we will have a quiz and assignment for lecture 3. Also, we'll have AC theory. This is and then after finishing AC theory, we'll have a magnetic circuit, as I told you previous definition. And in 15 and 16 weeks, 16 and 17 weeks, we'll have the semester examination. This is the calendar also I defined so that you can follow my program calendar, which I did here. Assignment be as you can see here. And that will be the end of our module. So let us now start with the lecture. Lecture 1. This is the basic electricity, whereby we are going to see the basics of electricity. So in basic electricity, we are going to see here we can see the atom. When you are studying the electricity, starting with the atom is a particle of matter that uniquely defines a chemical element, and the atom consists of the central nucleus, which contains negatively charged electrons and positively charged protons. The nucleus is positive charge and it contains one or more relative heavy metals, which are positive heavy particle known as positive neutrons. So you can see here atom is built up here. So when the atom electrons move, has a positive charge neutron, are neutral, and therefore have no charge, because electrons are negatively charged and the protons are positive. So atom itself are neutral. Say that atoms are electrically neutral. Current, the flow of electron is called the current, as you know. When the current flow in the circuit, you have the current flow in the circuit. The unit of current is the amps. Conventional current. In history, when they discovered these things, before they didn't know about the charges. They know that there's a charge, which is moving, but they didn't know if there's a positive and negative charge. So the only way it can work. So that's why today historical physicists did not know about atom and electron when they create the rule of electricity. They knew it was charged that moved, but they didn't know if it was positive or negative. they assume it is positive according to them. And that is why the rest of electrical rules have been biased on positive. Also, there's the electromotive force. In order to atom to move, they need the force. So this is called the electrical motive force. Battery and the source of power are examples of electrical motive forces. Potential difference. Potential difference is the difference between potential between 2 points. It's called the potential difference. When you've got the different EMF across the wire, the difference 2 points is known as the potential difference. You can see an example here that you have 5 volts supplied, but here you get 3 volts out. So where is the 2 volts goes? So the 2 volts is used to heat. This is the I give example from the original type of this lamp, which use the incandescent lamp. So filament heating, then they heat, they give light. So the 2 volts is consumed by the light. Resistance or resistivity. Resistance, not all material give up their electron to pass across easily. So remember that the metal give up electron easily, where there's non-metal not give away electron easily. This reluctance to give away electron is called a resistance. So it's called a resistance. Example of resistance is like here. We have resistance. Material with high resistance are not allow easy current to pass through them. There's high resistance like you can see here, like plastic material, like clothes, wooden chair. These are material which they not give easily resistance. But material which are easily or have got low resistance conduct, like metals and others. Then we have the power. Power is equal to work done times time, or work done, the work done. So work done is moving of electron from one place to another. Power is measured in watts. Power is equal to EMF, which is the force, times time. EMF times the current. And watt is voltage times ampere. This is the unit of power. So voltage times the ampere. Example, the power exercise, say power is equal to EMF times current, and therefore when watt is equal to voltage times ampere. What is the power of the bulb? If it goes to EMF of 2 volts and a current of 11 ampere. So what is the power of filament bulb? EMF of 8 volt and current of 11 ampere. So power will be equal to current, voltage times current, which means that this power here, it will give you 22 watts, and the other one will give you 88 watts. So it's an example of power. Electrical energy is work done in a period of time. Unit is kilowatt hour. Kilowatt hour is power times time. Power is kilowatt times time is, you get power times time, you get the energy. So in electricity also. But now you have EMF times current times time. This is the electrical power. Example of electrical, a grinder has in the Musi workshop, has a power rating of 800 watts. It runs for 20 minutes, and a session is used 2 times a day. Calculate the daily electrical energy that is needed in kilowatt hour. Length of time of a day is 2 times 20 minutes, which is equal to 40 minutes a day. So if you convert to hours, it will be 40 minutes over 60 minutes you get 0.66 hours. So electrical energy will be 800 watts times 0.66 hours. This will be 52 watts hour, or 0.52 kilowatt hour. Another example of electrical energy example is water pump. At Must workshop uses 4.4 kilowatt a day. It is 2 hours a day. It works for 2 hours a day. If the EMF of the pump is 320 volts, what is the current? Now you can get those relations from current and voltage. So electrical energy used in 1 hour is equal to 4.4 kilowatt hour a day. For 2 hours a day, that means 22.2 kilowatt hour, or 2200 watts. So electrical energy used in 1 hour, 22 watts. Electrical energy is called EMF times current times the time. So current is equal to electrical energy over EMF, which will be equal to 2000. So this is the example of energy. Another things which you are going also to discuss as a basic quantity of units. So those basic quantity of units are electrical charges. This is the physical property of matter that causes it to experience a force when placed in an electromagnetic field. The unit of charge is the coulomb, and the symbol is Q. Abbreviation is C. So this is the electrical charge. We have also electrical current. There's a direct current and the alternating current. So direct current travel in the same one direction, and the alternating current periodically reversed. We also have a resistance. The resistance is opposition of material to move. The resistance is measured in opposition to current flow in the electrical circuit. Resistance is measured in ohms, as you can see, and when the current exceeds the resistor, the resistance, when the current passes through the resistance might burn. So by burning the resistance, then they create something like fuse. When you create a fuse can be used as a protecting when you want some equipment to have not more than the certain amount of current, and therefore the fuse can be used as a protecting device. So here we're studying the fuse. If there's a fault in a piece of equipment, then the excessive current might flow. This will cause overheating and possible fire. So fuses protect against this happening, because when you have a maximum resistance, allow the current to pass. If the current is passing more than that, the current can cause the fire. Then the resistance blow and disconnect the system. So sometimes, we use the resistance as a protection mechanism. Current from the supply of the equipment flow through the fuse. The fuse is a piece of wire which can carry a stated current. If the current rises above this value, it will melt. Example of a fuse, we have the different type of fuses. If 5 ampere, 10 ampere, and 13 ampere fuses are available, state which is most appropriate of the following appliances, which are both connected to a 240 volt supply. So we have to find, normally we don't have a specific, size of fuse. We put like standard. You say, okay, 5 ampere, 10 ampere, 13 ampere, 25 ampere, etc. And therefore, for protection now, you have to select the certain amount of fuse which is closer to the fuse, to the maximum current which is allowed, so that if it exceeds, it can protect the circuit. And we know that power is equal to voltage times current, from which current is equal to power over voltage. So to solve this question now, what are we going to do? You say for the toaster, here we say toaster has got 1 kilowatt. So for the toaster, maximum current is power over voltage, which is 4.17 ampere. In that case, if you have 4.17 and in standard you have 5 ampere, 13 ampere, you remember, 10 ampere. So 13 ampere, 10 ampere. So automatically you choose the closest, plus or minus 1% or so. So 5 ampere fuse will be appropriate for that case. For fire, power is equal to, current is equal to power over voltage. Maximum current which pass through which generator which is coming from the fire, electrical fire, is 12.5 ampere. So for protection now, you put 13 ampere so that if it exceeds 12.5, that's maximum it can do. Now, if it exceed that one, up to 13, then the fuse should blow so that it will protect the system. Another problem here is another television set having a power rating of 120 watts and electric lawnmower of power rating 1 kilowatt are both connected to a 240 volt supply. If 3 ampere, 5 ampere, and 10 ampere fuse are available, set which is the most appropriate for each appliances. So now we do the same calculation to find exactly. We have the power, we have the voltage. So power, you can